are live from Cisco Research in San Jose and across the world. We'll be hosting a summit today, Cisco Research Summit on generative AI and security. I'd like to invite our head of Cisco Research, Dr. Ramana Kampela, to kick off the summit and speak a few words.
Thank you, Ashish. This is an amazing topic, and I think a very timely topic to have this PI summit on. And good morning, afternoon, or evening, folks, for all the folks tuning in from across the world. And welcome to the AI and Security Summit, Generative AI and Security Summit, where I'm so excited to that we get to hear from a very distinguished set of panelists from several top universities that are actively working in this area that intersects generative AI and cybersecurity. And as you probably already know, while it has been already, 5 years since the invention of the transformer models, the basis for generative AI, I think the field of generative AI has just gotten super hot thanks to the release of ChatGPT almost a year back now. And there has been a tremendous amount of interest in harnessing the power of generative AI in various day-to-day tasks, right, including things like programming, writing text, question and answers, information retrieval, what have you. The list just goes on. And the sky truly seems to be the limit here in the number of use cases that can be affected with the help of generative AI. And as with any new tech, right, there's always a concern that the new tech will be used in malicious ways that can seriously cause harm to one and all. And hackers are always looking for exploits and security gaps, to expose these new attack vectors. And understanding and studying these potential vulnerabilities is a key area for Cisco Research, led by Ashish and team. And I'm so super excited about this summit, just given the timeliness, and I'm really looking forward to some exciting presentations, discussions, and some question and answers around these topics. So thank you all for joining, and especially my sincere thanks to all the panelists who have made themselves available to participate in this summit. And thanks, Ashish, for bringing them all together and leading this session. So over to you.
Thank you so much, Ramana, for a great introduction and kickoff. And without Ramana and senior leadership support from Cisco Research and Cisco, it wouldn't have been possible to actually continue the exciting work that we are doing within Cisco Research on this important topic of research and development, as well as to be able to fund and sponsor these projects with our distinguished set of PIs. Some of them we have here to speak today. And I'll also like to thank the staff, especially Kim from Cisco TV, Ranis and Carla, who are actually organizing and taking care of everything in the back end to get this summit going. Thank you so much. So the agenda of this summit would be, as Ramana kicked off, I'll be speaking briefly on LLM security. Initially, I wanted to give a set of demos, but I think due to constraint of time and other aspects, we'll not be able to do that. Maybe we'll do that later, some other time. Around 8:10, and also Srini Devadas from MIT will speak on tech privacy, followed by Vijayalakshmi Atluri from Rutgers University. She'll be talking about policies and natural language text. And then Jie Ding from University of Minnesota will be talking about security of large AI models. And then Ravi, Sandhu, and Krishnan from UTSA will be talking about perspective on AI and security. Followed by, we'll have about 35 to 40 minutes of panel roundtable of questions and discussion. So I'd encourage all the audience to submit their questions, and so that we can have a very lively discussion at the end of the speaking schedule. Of course, at the end of each talk, we'll be able to have one question answered by the speaker. So feel free to submit your question also right before each speaker ends their talk. So I'll briefly go out, revisit the talk of Ken Thompson during our lecture in 1983. He talked about trusting trust. And it's quite relevant today to ask the same question, that to what extent can we trust the statement of a program that a program is free of a Trojan horses? Should we trust the people who wrote the software? Should we trust the software itself? And perhaps we should trust the people who wrote the software. Now the world has changed after about 40 years, that we do not have people who are writing software. Now we have LLMs who are generating code, writing the software. So perhaps instead of having people, we should modify the statement to maybe to trust the people, or GenAI who wrote, generated, modified the software, the models, artifacts, or data, right? So, and how would you ensure that you trust GenAI? Or large language models that implement certain capabilities of GenAI. So quickly, some of the questions that come into mind when we talk about trustworthiness and security of LLMs. Of course, this is not a exhaustive list. There's some of the things that we have been looking at, and also some of the things that come into mind. Are the LLMs protected against a reasonable threat model, right? In the context of application, what is a threat model that we are going to protect the LLM, and we are going to protect the application of that LLM. So that threat model is evolving slowly with prompt engineering, threat models, etc. Does the LLMs protect privacy for users across sessions, prompts, and responses? What are the caching semantics of these LLMs? And then are the LLMs compliance aware? Are they ethics aware? And are they fair? Are they consistent and reliable in their responses? One of the most important things that we have observed is that these LLMs are not consistent at all in their response to the same prompt, same query, over time, over sessions, over users. The spatiotemporal behavior changes, and therefore they are inconsistent, unreliable. Therefore, it's hard to trust them. And how fragile or robust are these LLMs with respect to security, privacy, compliance, ethics, and reliability? These are some of the questions that, like very basic questions, that we ask for any other system. We also ask LLMs. The question is why we're asking the same questions to LLMs, because this is another system being used by the world, or being engineered, customized, or even retrained by engineers and researchers to use them in certain contexts. Therefore, we need to ask from the same basic state of zero, or a basic state, origin state, and then see how secure they are, or how trustworthy they are, how private they are, right? So with that, let me start inviting our speakers. The next speaker is Professor Srini Devadas. Srini is a professor at MIT. He has been someone who has worked significantly in computer security, architecture, applied cryptography. His work has led to essentially the realization and implementation of PUFs, physically unclonable functions, and several other things. And we have been fortunate to be able to collaborate with him, to be able to work with him on PAC privacy. So he's going to talk today on PAC privacy, automatic privacy measurement, and control of data processing. Thank you so much, Srini, for your time, and over to you.
Thanks, Ashish, for the introduction and the opportunity to present. I'll go ahead and share my screen here. I have to say that first, this work was largely done by my student, Hanshan Shao, who's getting ready to graduate. So hopefully I'll do a good job of presenting his work here. This is a long title here, but let me cut to the chase and talk about exactly what it is that we're trying to solve in terms of the problem we're trying to solve. It's a very generic problem. We're interested in information leakage from arbitrary disclosure. And so you have some sensitive data. It could be messages, email messages, files, what have you, lung scan images, medical data, and you're going to do some processing on it. And again, very generically, we're going to call this processing algorithm M. And M could be simply the average of a bunch of salaries that are sensitive. So you're just computing the mean. M could be something where you are actually doing a training algorithm on sensitive data, perhaps even an LLM. And the actual output, M of X, is the neural network. So the parameters that are that correspond to the neural network that were learned from this training set. Or M could be side channel information that is leaked to an adversary, and you're concerned about a leakage from these side channels, and that leakage could discover something about X. Maybe there's a secret key inside of X, etc. So a pretty generic model. And the big question is, what do we mean by privacy at the high level when we talk about this this generic model? And just in plain English, without getting into the mathematics, which we will in a few minutes, we can say that we want to make sure that the adversary cannot guess or recover the secret, part of the secret, correctly or approximately correctly. The fact is that if you get 80% of a secret key, you can brute force the rest, right? So the approximation is important. And then we have to start getting more precise with respect to what kind of adversary are we talking about? Is the adversary computationally bounded? And that's a reasonable assumption. But sometimes you want to think about computationally unbounded adversaries. And then the big thing, which is a little bit even more involved, is what is the prior knowledge of the adversary? What does the adversary know about X? Does the adversary know that X is salaries, that the X are lung scan images, that they're network packets from a Cisco router, or what have you? And so that actually helps because it gives the adversary context. And that's been a big challenge with respect to defining privacy. So once we do that, we have to quantify the inference hardness. So what is the task of the adversary? Reverse engineering to get parts of X or bits of X, or in an approximate way, in an exact way? And how do we measure this? Are we going to say that it's impossible for a computationally bounded adversary to do this? Or there's some confidence with which the adversary can do it, and we can limit that confidence to 5%, 1%, negligible, or what have you? So a whole bunch of things to do. And as you can imagine, there's been a whole lot of definitions that have been used, and these are just a small fraction of the definitions. They're important ones and that have many variants. But there's Shannon perfect secrecy, which is the ultimate, which says that for any possible inputs X and X prime, the distributions of M of X and M of X prime are identical. So there's no way you can learn anything about X or X prime because of this property. And this is incredibly expensive, and it's basically impossible to do. One-time pads, give you that, but you can only use them in limited contexts and not for statistical processing. Computational indistinguishability is something that the cryptographers have used a lot. There's many assumptions associated with the computationally bounded adversary. The adversary cannot factor numbers, the adversary can't do discrete log, what have you. And again, it says for any possible inputs x and x prime, the distributions are such that they're indistinguishable to a computationally bounded adversary. And then finally, differential privacy limits the data sets, talks about individuals. So there's one individual that is in X and not in X prime or vice versa. And you look at the divergence of distributions under some divergence function. This is generally called alpha divergence, or if it was DF, it would be F divergence. And there's many different alphas and Fs. And I'll say a little bit more about it. But you say that you run this experiment over and over of generating M of X and M of X prime, present them to the adversary, and the adversary is going to be, maybe somewhat successful in distinguishing them or not successful at all. The difference between the distributions is going to give you a sense of how much knowledge the adversary has. The more divergent these distributions are, the easier the task of the adversary. So it's a measurement of adversary hardness. So path privacy is trying to bridge the semantic privacy interpretation to the mathematical world of numbers. So if you want to be able to say that with 99% failure rate, the adversary will be able to guess, or the adversary can only guess with a 1% success rate, and no more than that, things like that. And so for that, you have to do the things I just told you. So really quickly, figure out the public parameters. The adversary maybe knows that your secret images are about pets or portraits of your kids or what have you. Select the task of interest of adversarial inference. Oh, even if one bit is found, then the adversary wins, or the adversary has to recover the entire sample with some error in L2 norm, yada, yada, yada. And the idea is that we want to somehow take the output of M of X, that is the output of M, which is M of X, and we're going to try and make that private. And basically, we're going to make it private by adding some noise to it. We're going to perturb it. We're going to jiggle it. And that's going to be our strategy, but you could do other things as well. So one of the big ideas in path privacy is the separation of prior success rate and posterior advantage that I want to explain to you in just a minute. So we're going to assume that X is going to come from a distribution, and that's going to be the prior knowledge of an adversary. And I'll say some more about it as I go along. We're going to specify a target inference problem that I just described to you. And at this point, nothing has been exposed. The adversary knows the distribution, doesn't know X. And so if, for example, you're generating random numbers between 0 and 1, and you're supposed to guess the numbers exactly, well, the prior success rate in this case is essentially 0, because you want to guess the numbers exactly if the numbers were continuous. But if the numbers were discretized, to 0.1 accuracy, then the success rate would be 10%, because you can guess 10 values randomly with 10%. So that's all there is to prior success rate. Then the fun starts. You expose M of X, and you have to now measure the additional leakage. And together, the prior success rate and the additional leakage are going to give you the posterior success rate. And so that's our framework. We want to help you compute the posterior success rate given a prior success rate when you expose M. So that's our game here. So a little bit of math prep, not too difficult. We'll assume that the adversary is going to guess X tilde on corresponding to X, which may be exactly correct or maybe an approximation. We'll have a success criterion that says that if X tilde and X are close to each other, you can specify this any which way you want, then the adversary succeeds. So rho is a fairly generic function. We're going to have this optimal prior success rate. The failure rate is delta 0 rho, depends on rho, and the 0 just stands for the prior. And the success rate would be 1 minus that. So if we want the success rate to be low, the failure rate to be high. That's what hardness would mean. The posterior success rate is 1 minus delta. The failure rate would be delta. And that essentially says that even after seeing M of X, that's what the success rate or the failure rate is. So it's obviously different from delta zero. And the posterior advantage, which is a positive quantity, it only gets better for the adversary when the adversary gets more knowledge, is delta zero minus delta. Right? So delta zero is going to be greater than delta because the adversary now has more knowledge in the posterior case. So pack privacy is a term that's borrowed from probably approximately correct learning, which we just borrowed the terminology. It's a nice name. Pack learning was about how easy it was to learn or whether it was learnable. We are actually worried about the reverse problem. We want to make things hard to learn. And so think of it as pack hardness. So you have a data processing mechanism. I've told you most of these things. Delta is the failure probability, rho is the metric that corresponds to your criterion of distance, D is the distribution, and we're essentially saying you have these parameters associated with a particular M and D, etc., and that we want to tell you what the posterior advantage is and what the posterior success rate is. So that's all there is here. So now, well, a little bit more math. We're going to have to estimate delta. So how do we get to delta? Well, there are all these information theory quantities that relate to random variables to each other, to related random variables to each other, measure correlation, etc. And mutual information is this quantity that's been around for decades, really, that gives you a mechanism of telling you, what the relationship between two variables are. So you want to look at this and you say, well, you got two variables, x and w, and mutual information is defined as the divergence between two distributions, one of which is the joint distribution of x and w, and the other is the product of the marginal distributions of x and w. So the two bars that you see in the middle here correspond to the distance between the two distributions, and dkl is just a divergence function. I talked about f divergence, and kl is kl divergence, which stands for Kullback-Leibler divergence, which is a specific form of divergence, and that's not going to be particularly important, but that's what's being used to define mutual information. And you might have heard of perhaps a more natural definition of mutual information that corresponds to entropy, that says that the loss of entropy, when you see w, you don't know x, there's some uncertainty in x. When you see w, there's some loss of entropy of x, and h of x minus h of xw is the mutual information. So that loss is the mutual information. And these two definitions are exactly equivalent. They've been shown to be mathematically equivalent. So either way works. We're going to be using the KL divergence one for our numerical quantification. So I want to contrast pack privacy with existing means of measuring privacy. In particular, the most popular mechanism right now is differential privacy. So I'm going to do that using an example. So in pack privacy, because we assume that data is drawn from a distribution, we do not require a noise necessarily to show that hardness, to show that the adversary has a difficult job. So for example, let's take a case where you have n-1 IID samples, x1 through xn minus 1, and you're going to now generate another random sample, and you're going to publish the average of all of these n samples. Now, if you do this, and you compute the mutual information, and you can do this in a closed form, as you can see on the slide, you get the quantity over on the bottom right corresponding to the mutual information. So now as n goes to infinity, this mutual information goes to 0, which means that you're not really losing anything about x when you publish the average of a huge number of random variables, which sort of makes sense. Now, even when n is finite, or even when n is small, you do have bounded mutual information. So this is interesting. So this means that there is a level of hardness associated with even with finite n corresponding to this, this exposure of the average. And so this is what pack privacy would tell us. We could quantify the hardness based on this quantification of mutual information in this really simple example. And you don't have to add noise in order to get some level of hardness. If you added noise, you would get make the adversary's problem more difficult. That's certainly the case. Now, in differential privacy, you have a situation where you have to do, for the same example, you have to compute what's the global sensitivity I won't go into details, but it's just 1 over n in this case, where n is the number of variables you have. And you have this equation that essentially says that you have to add noise that is 1 divided by n times epsilon, where epsilon is your security parameter. Epsilon equals 0 would be perfect privacy. Epsilon equals infinity would be 0 privacy. But for a given n, in order to get essentially a finite epsilon, that would give you some level of privacy, you have to add some noise. Because if you add no noise, then given the equation that you see here for z, you would have epsilon equals infinity. So the highlight really here is that we're exploiting the entropy of the input data and computing the mutual information based on that entropy. And because of that, in packet privacy, there are cases where you add no noise, whereas in differential privacy, you have to add some noise. And this translates to being able to avoid what's called the curse of dimensionality. And I'll say a little bit more about that when I talk about the contrast a little bit more. So let me get to that. In differential privacy, you are independent of prior knowledge. You're really assuming that the adversary has infinite prior knowledge, knows everything about the data set except for the actual element that is being put into X and not in X prime or vice versa. So you're measuring the worst case likelihood. And this has wide applicability because it's very strong. And if you can show that posterior advantage is limited in the worst case, obviously it's limited in all cases. This is a distinguishability criterion. It doesn't really talk about reconstruction hardness. And the analysis for simple things like averages and so on for the global sensitivity is easy. But if you want to do complicated algorithms like machine learning, you have to break them up, and you can do only very simple steps and do analysis of global sensitivity for these very simple steps. And in general, for let's say non-convex optimization, the privacy security proof itself is NP hard to generate. And I mentioned the curse of dimensionality. Well, as it turns out, if the dimension of your output data is d, then there's a lower bound that says that you have to add theta square root of d noise in this adversarial data independent privacy case, which could be really large and grows as dimension. So when you have a neural network which has lots of parameters, the noise that you need to add to each of those parameters grows with the number of parameters. So that's not a good situation. In packet privacy, we're still talking about the worst case against an arbitrary adversarial strategy, but we assume a distribution, and so it's worst case that's instance specific to the distribution. So this is an assumption. We think it's a valid assumption to make for data processing, and it gives us some real advantages in terms of we can give an instance-based impossibility result against an arbitrary inference task, whether it's approximate or exact. More interestingly, we can produce an automatic proof, so we don't have to go through intricate human analysis and write really a different paper or need to write a different paper for every different algorithm. In many cases, you can add constant noise as opposed to noise that grows as the square root of d. And this really simple example of the Gaussian mean gives you some sense for why you can add less noise in packet privacy. All right. So let's talk now about bounding the posterior advantage. You have a situation where now you have any processing function, and I want you to focus on the very last line of the slide, and you can ignore everything else. It's a simple theorem that essentially says that the mutual information bounds the KL divergence of the posterior advantage. That's it. So if you can compute the mutual information, automatically, effectively, the posterior advantage that roughly you can think about as delta 0 minus delta, the extra probability with which the adversary can guess correctly, given that the adversary has seen MFX, is bounded by the mutual information, right? This is very nice because now we can give you an automatic way of measuring the mutual information. And we're also going to control this mutual information by adding noise to MFX. And when we do that, we can bound the mutual information, control it to whatever quantity we want, which bounds the posterior advantage, as you can see with this last line of this theorem, which is the special case of the theorem that's the most interesting, at least for this talk. The one cool thing about this is that we are doing this without committing to rho, which is that reconstruction metric. So we can say that for an arbitrary inference task, we'll control this mutual information by adding noise to it, and I'll get to that in just a second. And once we do that, the posterior advantage is control. The prior success rate definitely depends on rho, but that's separate from the exposure. You try to drive that down by having a distribution that is reasonably rich. For example, you have a guess between 1 out of 10 values or 1 out of 100 values, etc. And I'll talk about how we can reduce the prior success rate using subsampling before I'm done here. So what I have left to do is to do 2 things here. I want to tell you about how we can do automatic privacy analysis. I previewed it by saying that we're going to compute mutual information, which is a tried and trusted quantity. This theorem here that I'm going to get to in a second basically is going to allow us to figure out what noise we need to add to m of x, as you can see here, to bound mi x related to m of x plus b, where b is the noise. And what we want is a black box mechanism, and we can do that with Monte Carlo simulation and be able to discover this noise automatically. And we're going to do that. Once we do that, we bounded the posterior advantage. Right? So that's really the full picture. Again, a slightly hairy equation, but it's actually not that complicated. On the left-hand side, you have the mutual information corresponding to x and the perturbed output, m of x plus b. On the right-hand side, you essentially have something that says, look at the covariance of m of x, and I'm going to tell you what the covariance of the noise matrix is. Covariance is simply variance of multidimensional variables. If it's easy for you to think about single dimensions, then go ahead. Think about sigma m of x as simply being the variance of m of x when x is randomly chosen from the distribution. If that variance is large, we have to add more noise. If we are producing the same m of x for different x's, you basically have privacy by adding very little noise. That is the intuition. The variance of m of x is going to tell you how much noise you need to add, and we can do this whole thing automatically. So in general, these are covariance matrices if you have d dimensions. And all of this is really fluff. I don't want to get into it, but I want to leave you with this thought that you can avoid the curse of dimensionality because when you have essentially the covariance matrix, it may be the case that it's low rank, that the power of noise, or excuse me, the power of the variance is only in a small number of small part of the dimension space, small part of the space, the subspace, and it could be the case that this low rank thing would have order 1 power as opposed to order square root of d power. But either way, we can fit the noise to the geometry of the distribution and essentially add noise anisotropically, and it could be order 1 noise. Right? So overall, we now have an automatic protocol, and this protocol is going to add less or more noise depending on what the variance of the output is. So really quickly, we're going to sample.
Srini, sorry to interrupt. I think we're out of time almost. We have only 1 minute.
Okay, great. I'll finish in a minute.
Questions. Yeah.
Sorry. I'll finish in a minute. So I want to end with this algorithm, which is only in the next couple of slides, is animated, and we are going to sample x from this distribution. We're going to compute m of x. We're going to compute the covariance matrix, like I just said. We're going to find these eigenvalues and eigenvectors, and this is going to allow us to figure out what the noise is. And then the last step of this, which is my last slide here, is we're going to compute the necessary noise in each direction based on this covariance matrix, and we're going to generate anisotropic noise. So this m of x plus b is basically what you expose. So I basically presented the theory for you, and what we're doing now, and this is a separate talk here, which I can give maybe at a later review, is applying this to everything from ImageNet training to statistical processing, like finding the means and the variances and so on and so forth, and also unsupervised learning like k-means. So I'll stop there and take a question from you, Ashish, or anyone else. And sorry to go over by a minute, but thanks for the heads up. So.
No, not at all. No, thank you so much, Srini, for a great talk on PEC privacy and a general theory of privacy. It's an honor to have you on the summit here. So one quick question, there are a couple of questions that will come up. One of them is how PEC privacy is relevant and practically useful for LLM privacy or LLM security.
So so the way this would work is really quickly is LLMs are very time consuming in terms of machine learning. But what we have done so far is to be able to do something like ResNet training and be able to say something like the ResNet trained network that is recognizing images can be made private to not expose the sensitive data that came that was in the training set. So, and very simply, what would happen is you would run the training on subsampled input. You would compute the variance associated with the machine learning models across these different trials, and that would tell you how much noise you need to add to the machine learning model in order to privatize the model, right? And so now, of course, I mean, this LLMs are a different bucket. You could do this theoretically. The challenge is you now have to train these LLMs on different subsampled inputs many times, and obviously, that is a computational cost that you may or may not afford. And we're looking into improving that, but we can certainly do that in the medium scale, if not the large scale. So maybe MLMs as opposed to LLMs, right?
Yeah, thank you. Thank you so much, Srini, and we will come back to other questions in the panel. Now we have the privilege of inviting Professor Vijayalakshmi Atluri from Rutgers University to deliver a talk on generation of machine enforceable security policies from natural language text. Professor Atluri is a professor of Rutgers University, is an IEEE fellow, and has worked significantly over several decades in security policies on workflow security as well as distributed system security and database security. So without further ado, let me invite Professor Atluri for our talk.
Thanks, Ashish, for the great introduction. Can you all hear me?
Yes.
Yeah. I'm going to talk about one of the projects that we have just started on large language models, how they can be actually useful in generating automatically some security policies from natural language documents. So this is joint work with Professor Shamik Sural from Indian Institute of Technology, Kharagpur. So let me begin. So as we all know, these large language models like ChatGPT, it is like a two-edged sword. You can use it for beneficial purposes, or as earlier mentioned by Ashish, it can also be used in the negative connotation. For example, I was actually serving on a program committee on a security conference. Indeed, very recently in the 2023 conference, there were 2 papers that were submitted, were written by ChatGPT. And fortunately, the PC members were able to recognize them and were able to reproduce. And of course, they were rejected. But I'm going to talk about how tools like that can be actually useful for enforcing, configuring, and automating the process of security. So in this specific context, we are working with how to generate attribute-based access control policies. So ABAC is the next generation access control model. I'm going to give a little bit of introduction of how it actually evolved, how access control indeed evolved from the very primitive version to current ABAC, and why this automatic discovery is actually needed, and some of the recent attempts and our approach using LLMs to do this. So when you think about access control, a very, very brief overview of this is when you think about early 70s, there were models like discretionary access control, where users at their own discretion can allow other users access the resources that they want. It's a very flexible way of doing or controlling access. And also at the same time there was mandatory access control where users and objects, rather subjects and objects, are given security labels, and there are rigid rules on who can access what based on the labels of the objects and based on the labels of the subjects. So people, while DAC or discretionary access control was quite flexible because users can do what they want, and give permissions on their resources, MAC was considered as very rigid, and access control is not in the hands of the owners. So later on came role-based access control, which has a flavor of both DAC and MAC. Some of it is discretionary, some of it is mandatory, and where here a group of permissions are grouped into roles, and a user assumes a role, and by invoking a role, a user can gain access to this. And several extensions have been done to all these models since 95 to until 2014. Then the next generation access control model was presented, and it is again based on subjects and objects like users and resources. But the access permissions or policies are defined based on the attributes of the users and attributes of the resources. So I will just compare the whole spectrum here. So when it comes to the left-hand side, the discretionary or mandatory access control, they are from the administration point of view, from a security administration point of view, they are very heavy. Whereas if you go towards the right, where you go to the attribute-based access control, they strive to automate this process and they are more adaptable. Again, when it comes to DAC and MAC, the policies are rather fixed, whereas on the other hand, on the attribute-based control, access control, they are more flexible. Typically, DAC and MAC are organization-centric, whereas attribute-based access control, it lends itself to cross-organizational sharing of resources. So this is, I just want to give you a brief overview. Now let me focus more on what exactly is this attribute-based access control. As I mentioned earlier, the security rules are not based on user IDs or object IDs. Rather, they are based on attributes of the users and attributes of the objects, and also the environmental attributes. So policies or rules are defined based on this. Let me give you actually a very quick example. So for example, a doctor who is a cardiologist. So here you are talking about subject attributes. User is a doctor, that is an attribute. Cardiologist is an attribute of the subject, and they can access records of patients. So patient records is an attribute of the object or resource of the cardiology department. These are the records of the cardiology department. So this is an object attribute, and the environmental attribute is maybe the time, from 9 to 5, they can access in either read or write mode. So you can think of rules like that. For example, there could be a video library, and you may want to have a policy saying, security policy saying, oh, I have movies that are rated R can only be viewed by users who are 21 years or older. So here you're talking about resource attribute, that is the rating of the movie, and subject attribute, that is the age of a person. So that is what actually decides who can access what, rather than the actual user ID and the actual object ID. So that way that's why it is very flexible, and there is really no administration cost when it comes to maintaining these policies. So in a sample scenario, in a ABAC scenario, suppose if you want to enforce a particular policy, all you need to do is a subject submits its own attributes, and based on the access policy, rules are actually enforced. The access policy rules are based on object attributes. So a subject wanting to access an object, these attributes are actually play a role in deciding whether she can have access to that object. So the benefits of such attribute-based access control, because these are not based on user IDs or object IDs, it's very it is very portable type of access. So this is identity-less access. So they're very suitable for cloud computing, for example, or collaborative systems, where you don't need to have any user ID. You just need to get the attributes of the users. One can think of attributes as credentials of users, for example. And as we have seen through our examples, these can actually encode real life security rules directly, and they can be encoded and enforced. So this is a dynamic, and all these benefits compared to the well-accepted role-based access control policy, which suffers from role explosion. That means the number of roles are typically quite high. This minimizes those disadvantages. And also, as I mentioned, the administration cost or maintenance overhead is very low, because when we need to maintain either role-based access control or traditional user ID-based access control, you need to keep updating, so the administration cost is quite high. So as such, this has become the next generation access control model, and there is a NIST standard for this as well. So now let us actually come to the actual problem of how do you automatically discover these ABAC policies. In general, for enforcing any access control, defining these access roles is perceived to be the very expensive task. So there are actually two different approaches to define policies, these security rules. One is a top-down approach, where you know what exactly are the security requirements, and through a manual process, you look at the security documents that are there, interview people, and then come up with these security rules saying who can access what. Alternatively, there is an automatic approach or a bottom-up approach, which we call it as mining, that actually uses current access control, or rather the permissions that currently you have, and then somehow mine the attribute-based access control based on the current state of the affairs. So that means here, why do we actually need, what is the benefit of doing mining? Suppose if the access rules are using DAC, MAC, or RBAC, then if you want to go to a more flexible policy, transition to a more flexible policy such as ABAC, this mining actually helps you to do this. And also if a new user joins or a new object is added to the system, just by simply observing the attributes, you can actually give them access without having to really change any of the policies. So let me give you a brief idea of the mining, the bottom-up approach. So here, essentially, as I mentioned, you take the current access control permissions like user IDs and object IDs and what permissions they have. And here is the relation which is called user attribute relation. That means what are all the attributes that are assigned to a particular user. So you take all your users in the system and list all their attributes. Similarly, you do that for objects. So this is an object attribute relation. And we have this ABAC policy mining algorithm that generates these ABAC rules. And we make sure that this is a minimal set. So that means we remove any redundancies and make it consistent. And the essential characteristic that the discovered rules should have is they are an exact replica of the authorizations you begin with. That means you don't give more permissions or less permissions. So this is the bottom-up approach. And there have been many, although this was our own approach, but there have been other people, including the people in this group, are working on this problem. So now let me come to the project that we are doing here. So we talked about the bottom-up approach and the top-down approach, right? And we thought that the top-down approach is a manual process and you need to do, that's why it is so expensive and time-consuming. So now with this, in this particular work, what we are trying to do is, how can you actually automate this manual top-down approach and discover rules, or rather extract the rules that are expressed in natural language like English and translate them into enforceable security policies that is using attribute-based access control policies. So in this project, so we call those natural language access policies NLACP, and then we that are either semi-formally or formally, informally written in a natural language, and we are trying to extract them using specifically ChatGPT model, and then we our goal is to actually translate them into enforceable code that can be readily used and embedded into an access control system. So we have just started this project in August, actually, last couple of months ago, and we made some progress for this. So essentially, the input that we give is, of course, the natural language policies in English. And we also give the set of attributes that it has to extract. And then we have to, as we all know, whoever we are using, whenever you use these large language models, you have to give some suitable prompt to it so that it can actually do what you are asking it to do. So the output will be the attribute-based policy, and we translate that policy like the set of attributes of the subjects and objects, into a machine readable code such as extensible access control markup language, XACML, which is one of the standards now. So this is essentially what we are doing in a pictorial form. So these are the natural language access policies. We feed them to this LLM and the ABAC rules are generated. And we make sure that they are consistent. That means if there are any conflicts, we should be able to identify those conflicts and remove them. And they are made or translated into enforceable rules. So these are very preliminary results that we have as we have just started this project. The input we give as a natural language text. So for example, students are allowed to access this lab 2 on weekdays. So this is a natural language text, and we give a set of attributes that we are expecting to extract from it. For example, the label, whether it is allow or deny, a role, department, action, day, time, resource. And then the prompt that is we have tested with is, this is the one that is in pink. And this is what we have generated as an output. And after doing some post-processing, we are able to translate, or rather this one express this more into closer to XACML type expression. So this is, although we have a very, very preliminary result, it has several things that we are currently working on. Currently, the natural language text that we are providing, all the sentences that are we are providing are related to the access control sentences. It cannot actually discover or extract rules if we have a non-access control sentence there. So we are working on how to actually ignore identify them and ignore these non-security relevant sentences. And another thing that we are improving on is, currently we have to give a set of attributes that we are expecting to be in the output. And we want to get rid of this limitation, and we want to use it how to automatically generate these attributes without feeding these in the first place. And then we are working on employing machine learning algorithms like random forest and techniques to generate the actual ABAC rules from these, and try to identify any inconsistencies and so on. Finish in a minute. And then we want to find out the minimum set of policies. Suppose if there are redundant rules or one covers the other, we should be able to get rid of them. And then, as I mentioned earlier, we will generate this into XACML. And another thing is, how do we know that the ones that we generated are actually correct? That we want to regenerate natural language from XACML policy and also do the performance evaluation. So I would like to acknowledge funding from Cisco, and our collaborators are, as I mentioned, Shamik Sural already, and Ashish Kundu from Cisco Research, and one of our PhD students, Mian Yang, is started working on this, and Kajori Ghosh, a master student, working on this project. Thank you.
Thank you so much, Vijay, for a great talk on LLM-based policy generation. So one of the quick question that is coming up is, can you have a live demo on this?
Sure, we have We have a demo, but maybe we can show it to you after
Sure.
is here, you know. Yeah.
Yeah, maybe we can have a recorded
We
demo.
have
and
a
share
short,
it with the
small,
audience.
yeah, we do have something, but
Thank you. And the other problem is about consistency or I'm sorry, the conflicts between these rules that are generated in the policy using ChatGPT. How do you think that you can address that those inconsistency or conflicts that are generated?
yeah, so I think this is not a new problem. We have worked on this earlier as well, but that is the conflicts were arising due to inheritance, and one policy says you can access, and the other policy says you cannot access. So these are the things that we would like to first identify. Uh, uh, Once we generate these ABAC policies, um, um, then you just need to identify whether given a particular policy, this is the one which says given these set of attributes you can read this. There is another policy given this or a subset of the or a superset of these attributes, you cannot access it. So that is really a conflict that we are looking at.
Okay, thank. And the other question that is there is, how do you think the current large language models like ChatGPT is going to address some of the real challenges of policy generation, like what are the research challenges out there that ChatGPT should alleviate?
Yeah, this is actually a very new area. Until now, actually, I think Ravi can also speak about this as well. Until now, the manual approach of top-down extraction of access rules was really not an option because it is very expensive. It requires manually somebody reading through these and generating these access policies. Right now, we have the hope to actually automate this process. So earlier in organizations, typically you interview people and get these policies defined in your system. So typically the people who administer or the security administrators, they have very little knowledge of the actual domain. So they need to interview the domain experts in the organization to actually extract these rules, security rules, and configure these rules in a correct manner. So now we have the hope that we can probably automate or semi-automate this process. And once we have the rules, we can then verify that manually through the actual domain experts. So you are cutting down the cost of this, I am hoping, significantly. So that is what I'm hoping for. Of course, there are many things that need to be worked out, so this is, I believe, is just the beginning.
Okay, thank you so much, Vijay. And I think we'll come back to other questions in the panel discussion. So no, thank you so much, Vijay, for being with us on the summit, and we'll come back to you and others for the panel discussion. In the
Thank you.
meantime, let's go to Professor Jie Ding. He is an associate professor at University of Minnesota in the Department of Statistics, and he is someone we have been collaborating very closely on backdoor attacks as well as LLM specific security. So, Jie, over to you. It's a great pleasure to have you in this Cisco Research Summit here. Jie, are you able to? Like speak.
Can you hear me now and see the screen?
Yes, we can see your
Cool.
screen and we can hear you. Over to you. Thank you.
Thank you, Ashish and the Cisco team for having me here. It's my great pleasure to present some of our recent work. So in today's short presentation, I will quickly go through some major challenges we believe related to the security and the scalability of the large model training. So I will talk about the four, what we believe, fundamental challenges that are largely underexplored from both theoretical and algorithmic perspectives. The first is about teacher-guided learning. So it's empirically known that if we use teacher-guided labels instead of ground truth, usually independent labels, we are learning much faster. But what if the teachers are biased or even adversarial? And the second is about the scalable training and deployment of large models, especially in the online continuous setting where we have a single path of streaming data. How do we learn better and better without forgetting the past? The third is about the decentralized learning, that is about the multiple learners in a coordinative way learn something that is performing as if a large model. The last is about evaluation, assessment of model, the potential deficiency or risk, which is somewhat underexplored given that most of the attention is based on the accuracy. We want to understand actually how much deviation a model is from a theoretical limit, if there is such a well-defined limit. So I'm going to talk about what our team is working on, and especially the high-level ideas that we formulate and address them. The first is about the challenge from learning from the teachers. So it has been empirically observed that if a student learner is learning from a soft label, like a panda with probability 0.9, instead of a hard label, like it is a panda, from some pre-trained teacher, that student can learn much faster in terms of the rate of convergence. And it has been widely used in deep learning, especially model compression literature. So the question that we want to understand better is whether we have when we will have a gain in terms of the learning curve, or we might pose some risk that we don't want. So I'm going to talk about a very simple toy example first, just to give the insight. Let's consider a simple regression problem. So the teacher is already a pre-learned regression model that maps from RP to R. And what the student wants to do is to learn from the teacher, the underlying function. So we define the quantity, the sample size n here, to be the sample size needed for achieving epsilon closeness to the wanted function f. So student trying to learn as well as the teacher, but subject to some mechanism that how the teacher is going to respond to the student, right? The teacher could impose some bias, or the teacher is itself biased. And the A here is the student's learning algorithm. It will definitely depend on how the student is going to reconstruct the model, here represented as a supervised function. So first of all, we studied whether we can indeed have a gain from theoretical perspective. So we verified the folklore by studying several classical learning algorithms like regression, k-nearest neighbor, and kernel ridge regression. And indeed, we can learn much faster if the teacher is a nice teacher. The problem is that what if the teacher is not that great? So we still want to learn, but we are not quite sure how much intrinsic bias or underlying, the quality of the teacher. So we define a concept. We say a teacher is adversarial if the needed sample size, the cost of learning for the student, is much larger than acquiring from nature. So the idea is that if the student is even slower from a teacher compared with learning from IID, ground truth label data, then why not just learn from the nature? So Following this definition, we further define what we call adversarially powerful and most powerful. What it means is that a powerful adversary would mean that the student would rather learn from the nature because the ratio of the sample complexity will be asymptotically infinity. And most powerful means there is no teacher that is even worse than this teacher in terms of the rate of convergence, because this teacher is already pretty bad. So this is what we set up to understand the limit of the risk. And here is a snapshot of our results. We found that, for example, for k-nearest neighbor, the constant shift is actually not only most powerful, also most powerful. But for kernel ridge regression, the constant is not. By constant shift, I mean add a constant perturbation to the outcome of the teacher-generated label. So we actually have our own way of the construction and show some most powerful perturbation mechanism. The high-level message is that we need to have some sophisticated joint-dependent perturbation rather than IAD perturbation. So behind all these results is actually a theoretical framework that we set up to understand the machine learning generalizability from a totally different perspective than the classical way. So we say a teacher is DNAN adversarial, where the D here means from defense perspective. The perturbation is very small, but the generalization error is at least greater than AN. So the message is that we actually want to have some we consider some dependent agent E here, that we create a setup that we have a small training error, it is small injected error, but we have a huge generalization error, so that the teacher is adversarial, mislead the student. So we want to understand whether this is possible and what is the limit there. So it's different from the classical learning theory, where we study a small training error plus some reasonable complexity will give the small generalization error. We are doing the reverse, right? We want to have a large generalization error with a small training error. So we studied some toy example here. I just want to demonstrate what it looks like. So here is a quadratic function, and we perturb as the blue dots. If we perturb in this way, we actually theoretically show that if the guy is doing if the student is doing a polynomial fitting with some standard information criteria as the selection criteria of the degrees, then the teacher can successfully mislead the student by tricking the student overfit. The idea is to overfit. The perturbation is added in such a sophisticated way, actually it's theoretically derived, not random, so that the student will overfit a higher order polynomial and therefore create a disaster during the generalization. This is the idea. And interestingly, it's also related, fundamentally the same as our newly proposed model privacy framework. I'm not going to talk detail, but just want to highlight the connection here. When the teacher is adversarial, from the other angle, we can actually say the model is private, right? If we have a nice defense mechanism against stealing attack, we don't want the model to be stolen. Then we can actually perturb in that way, as if we want an adversarial teacher. So this is the connection. What is worse is that the teacher can actually provide both the noisy input and output. So previously we had some insights of the input perturbation alone. But if the output can also be manipulated, it will be, for example, something related to the backdoor. That is a very serious security concern in large models. The large model usually means it's expressive enough to handle different kinds of data inputs, right? So it's actually, a concern when we consider large capacity of the model or the large alphabet of the model output space. So we just did some pilot study on the ChatGPT, and we just fine-tune it and see whether it is easily backdoor. So indeed, so basically what we showed is that, I will just give you the detail. The message is that with the fine-tuned model, fine-tuned from the GPT, we can easily backdoor it with maybe only hundreds of backdoor labeled data. The backdoor here means we just say the stop sign to be, speed side. Okay. So we had some understanding there, but the main message is summarized here. So we found that we first of all postulate what we call adaptivity hypothesis. What it says that as long as the model meets this criteria, that if we have new data, new training data, that is somewhat in probability sense far away from the original training data, then the decision boundary can be easily flexible to adapt the new training data. So we can visualize that the decision boundary here between this red and blue are not changed much, but the decision boundary here is accommodating the new discrimination we want for this orange new data. And based on this adaptivity hypothesis, we then understand that a backdoor is most effective when the input perturbation is in Euclidean distance small, but in probability distance large. So inside is illustrating this figure. So suppose we have a Hockey and auto classifier, and they have two directions on this 2D plane, right? One direction has large variation, the other direction, vertical direction, has a little variation. So in that case, we perturb the Hockey, we backdoor the auto to be Hockey in this direction. So in this way, we can easily manipulate a little bit the decision boundary so that it can accommodate a new label without compromising the previous accuracy on the typical data. So this is the high-level insight. And based on the insight, we had some theoretical derivation, but basically, it's not only happening on deep learning models. As long as a model will have that flexibility, like kernel, we showed that for kernel-based model, it will be easily susceptible to backdoor attacks. And furthermore, based on the understanding, we derived some defense strategy because we know likely the attack is going in that direction. So we would just defend against that direction. So we set up a hypothesis test-based defense mechanism, and we recently showed it will outperform all the state-of-the-art defense mechanisms and also effective against the 12 popular backdoor attacks. Yeah, so the second challenge I want to highlight is about scalable training. We all know that it's very expensive to train models. It's especially difficult to maintain when the data are streaming, because we don't even have the data storage for storing those data, right? So here, motivated by humans learn, our team is developing what we call an adaptive continual learning approach. So the human learns math, physics, chemistry in a way that is not only recurring, but also reinforcing each other, right? We learn math better and better instead of forgetting the math and then learn the new math again. So we want to actually formulate this problem as a continual learning problem. So in the literature of continual learning, a fundamental challenge is about so-called catastrophic forgetting. What it means is that when we learn new task, we forget the previous one. So we approach it in a little bit different way. So we want to, first of all, formulate in a way that we actually count for the recurrence, because we learn math in different levels, not only just to learn every new subject every day, right? We actually want to not only forget, but also learn better and better. So we want to study, based on that, the fundamental limits of the trade-offs between adaptivity to new task and the forgetting that we forget the previous task, and the algorithmic approach. So here, I will just very briefly talk about the setup. The setup is that we consider different segments. Each segment will have IID data from some distribution, and there will be some change between these segments. So we don't know three things. We don't know the distribution, because that's related to task we want to learn. We don't know the task boundary. We don't know when the task already changed. The student is working hard or is learning some new subjects. And we don't know the identity of the task. So here we assume there are say M equals 3, math, physics, chemistry. We only have 3 subjects to learn, but we actually have like 1 million segments. So how can we adaptively figure out that, oh, there are only this amount of small number of subjects that are core concepts, and we don't want to waste energy learning something new from scratch. We want to actually use that to learn better and better, right? So this is a setup we have. Mathematical framework. And then we study that, and we want to understand two fundamental problems. Like first, how do we have some belief that we learn at the end the subjects that are core subjects? So we want to learn the number of true distributions, unique distributions underlying all these heterogeneous streaming data. The second is how do we optimally use the knowledge, optimal in the sense that we achieve some kind of optimal cumulative loss when we do the sequential prediction along time at any future stopping time. So this is what we want to achieve. I would, instead of details, I'll just highlight the main message. So the main message is that we have an algorithmic way and theoretical construction that features two types of learners that we found necessary. So one type of learner is what we call fast learner. The fast learner's job is to adapt to new tasks and perform prediction. The second is slow learner that try to absorb what has been learned and then consolidate it so that it can facilitate the fast learner in the future learning. Whenever a new task comes, we first identify whether it's an existing task, or if not, we create a new one. Right? We need to do this, but not in a very hard way. We don't want to do change detection and then do the hypothesis testing to merge them and then do the refitting. Because it's online setup, we don't want to do all these things again and again offline. So yeah, so here most of the challenge is about how to set up the algorithm in an online way. So we don't need to store the historical data. Instead, we store the slow learners. So in the large model setup that we are actively working on, we can think the slow learners as small models. So this actually provides a way that we train large model by training small models, but in a way that coordinate them, interweave them together. So this is the direction we want to move to. Yeah. So I will just skip these details, but I want to just highlight that one of the theoretical results is about the prediction loss. That the dominating term actually will reduce from K to M. K is the number of segments. K is the number of data sets we can think. And M is the number of true subjects, the unique core concepts we want to capture. So we adaptively achieve that tighter bound by getting rid of the K. And in terms of knowledge, we want to have some kind of consistency that the learned concepts will converge to the truth if we set up a truth in that way. Yeah. So this is just a demonstration of the experiment result that we basically outcome all the state-of-the-art continual learning approach with our red curve. Okay, so next I will, given the interest of time, I will quickly talk about the two other challenges very quickly. One is about the decentralized learning. So this is about the multiple organizations work together to figure out a task, but this task usually is private. In practice, we often see the setting where a company will protect not only data. We had a lot of concerns in the data privacy, but I want to say that model and objective are sometimes also private. And they are also very important concerns during the collaboration, the learning. So how do we have a way that we exchange information without sharing the data, model, or task, but still can get the job done for any of the organization? So this is a high-level challenge. Some of our pilot study was about that we proposed was to approach this from a functional space perspective. So what we do is that we run a functional gradient descent instead of a model parametric model-based optimization. And then we outsource the direction of reducing the loss in abstract.
Interrupt.
Sure.
Yeah,
I
we
got
have about a
one
minute
minute.
remaining. So I just want to make sure that you're speaking focus on LLM just before we taper off. Yeah, thank you.
Yeah. So here the idea is to outsource the direction of reducing the loss to other organizations. So recently we actually worked on fine-tuning LLM using this approach that we consider different organizations, and what they do is that instead of sharing the data and what they are doing, they basically outsource the direction of the direction of reducing the loss for other organizations to fine-tune locally. So this is a high-level idea. The last one is about diagnostics. I'll just quickly say the problem. The problem is that we want to understand whether there is a deficiency of a model in terms of whether there is a statistically significant deviation of the learned model and the oracle as specified by the probability law. Certainly, we don't know the law, right? We only given the data. So we want to know whether there is such a discrepancy. And accuracy alone is not enough to solve that, because 99% accuracy seems high. But we want to understand whether we can achieve 99.99, right? So we want to understand that part. Yeah, so I will skip this approach and quickly summarize that challenges that we talked. Firstly, about teacher-guided learning, and then about what is the most adversarial setting of the teacher learning, and the backdoor attacks and defense. And following that, the continual training of the model from online learning perspective, and then the decentralized collaboration, and finally, model agnostics. So these are all the challenges we believe that we need to spend more effort on. Yeah. I would like to acknowledge all the collaborators, especially our Cisco team that contributed a lot to part of the presentation. Yeah. Thank you very much.
Thank you so much for your great talk, and we have several questions. One of them is actually on how the continual learning and other different attacks that you mentioned, or LLMs.
Right. Yeah, that's an excellent point. So I mentioned that our approach to handle the continual learning is to train multiple small models as a surrogate of one single large model, because the way that we set up, right? Okay, then more easily maintain the security by approaching each of the small models. So this is our strategy.
Okay. There's another question on how can we simplify the RAI, or responsible AI process. Today it takes more time than evaluating the LLM models.
Right.
And would it be possible for you to shed some light on that?
Yeah. So there are generally at least two problems of scalable training. One is about how to train a foundation model from scratch. The second is about how to fine-tune a foundation model by adapting to a particular data domain. Right? So these two are a little bit different. So the first, so certainly our continual learning aim to address both of them. First of all, when we train from scratch, we don't know what data are high quality and how the heterogeneity of the data can be split, right? So therefore, it's reasonable to split the data in a way that we believe there is some recurrence that we want to capture. But the data in the long run will be heterogeneous. So we want to set up a problem as I presented, so that we don't forget the capability learned from historical data. So that is one setting. The second is a fine-tuning setting. It's more related actually to the decentralized learning I mentioned. So the concern there is that usually there will be some privacy concerns between the service provider and the data owner. The data owner really wants to fine-tune the model, but it doesn't want to upload the model. And the large model is just too large to copy paste to the local machine to run. So there is this challenge of and the need of decentralized learning. Yeah, so that's my current view. Thank you.
Thank you so much, Jie, for your collaboration and also for the great talk again right now here in Cisco Research Summit. Now I'm going to invite Professor Ravi, Sandhu, and Professor Krishnan for their presentation. And it's a great honor and privilege to have Ravi on the speaking schedule here, and along with Ram. Thank you so much for your time. So Ravi is the inventor of RBAC, role-based access control, and he is an SCM fellow and a fellow at AAS fellow and National Academy of Inventors fellow. He is very well known for his work in security for several decades. especially on access control. We have a project with him and Ram on deep learning for access control, and on this specific talk they'll be talking about on how LLMs can be used with respect to access control and other security policies and security capabilities that can be enforced. Ram Krishnan is a professor at UTSA. He is a Microsoft President's Endowed Professor and is an associate professor ECE in UTSA. He also has been very kind to collaborate with us, and look forward to Ravi and Ram's talk. Over to you, Ravi and Ram. Thank you.
Yeah. Thank you, Ashish. And thanks to Cisco Research for organizing this and giving us this opportunity. Our project with Cisco and Ashish has just begun, focusing on deep learning applied to the insider threat problem. So we don't really have much to report on that right now. Certainly in some later occasion, we'll be happy to do that. Also, Ram will not be joining us for the talk, but he will be available for the panel, which is going to follow my talk. And I should also mention that he is now a full professor. So Ashish introduced him as an associate professor, which I guess is also right.
So my apologies. Sorry for that.
I'm going to give a very high-level perspective on.
Ravi, sorry to interrupt. Is it possible to have your camera on?
No, I don't have a camera ready here.
Okay. Sorry, yeah, let's go. Yeah. Thank you.
So as I was saying, I'm going to give a very high-level talk and presentation on sort of the big thoughts on AI and security. AI is definitely changing the security landscape. And there are other evolutions in security because of the complexity of the security domain with cloud computing, Internet of Things, decentralized computing with activity occurring almost everywhere across the planet concurrently. So there is a security challenge, and then there's AI, which brings a two-faced impact on the field. On one hand, it can aid the attacker. On the other hand, it can aid the defender. And we are kind of not yet sure which one is going to be more impactful in the long run. So as AI permeates the attack space, we cannot just continue to defend it as we have been doing using human defenders. So just continuing in this mode is going to be hopeless. However, our hope is that we are going to inject AI on the defense side also. And in some ways, that's our only hope, because if we don't do that, we are just giving up on the problem. And we have generally recognized in the security business that the attackers have an intrinsic asymmetric advantage. The attacker has to find one vulnerability or one way of getting in, whereas the defender has to protect everything. And that's a lot harder to do. Protecting everything is a lot harder to do by definition. So how do we flip this asymmetric advantage? And can we use AI to help us do this flipping? Or is AI going to make this asymmetric advantage even worse? That is a fundamental question. And traditionally, we have acknowledged the asymmetric advantage of the attacker. Maybe saying one vulnerability is a little oversimplification, because a sophisticated attack tree may require the attacker to exploit a series of vulnerabilities before they reach their target. But still, it's only one path in the attack tree that has to succeed. And the defender has to worry about attacks against vulnerabilities which have not even yet been found by the defenders. So it's very hard. Security becomes a super hard problem because of this intrinsic asymmetry. Now, if we bring AI into the picture, there are two aspects to good AI. We need good data and we need good training. And suppose we say that as far as the training and the nature of the models go, maybe the attacker and defender basically have a symmetric situation. Now, this may not be always true if the attacker has got much less resources than the defender. But, we have to worry about sophisticated attackers, nation-state attackers. So I think it's a reasonable assumption to say that the intrinsic quality of the models is not going to really confer an asymmetric advantage on either side. So the advantage, if any, is going to flow from the data. And if the training is symmetric, any asymmetry is going to come from the data. So what can we conclude? If we want to take advantage to the defender, then we must have good data for the defenders. If we have poor data for the defenders, we are not going to be able to succeed in this quest that we have of trying to flip the asymmetry of the attacker. So what is the data problem? There is a data poverty problem because as defenders, there is a lot of data, but a lot of it is held very closely and not shared openly. And especially when you look at academic researchers, there is a clear data poverty problem because there is just not enough data to test their theories and models on. But even if you have a lot of data, in fact, even if you have super abundance of data, you're going to have this good data recognition problem because data can get polluted. And how do you know which data is reliable and which is not? So to me, that is somehow in the long run going to be the fundamental problem of who gets to take advantage of the asymmetry between defense and attack. And drowning in data can also leave you drowning in bad data. I will make note of this so-called Brandolini's law, which was postulated in 2013. It's also known as the BS asymmetry principle. I'm not going to spell out BS. It is a family-friendly forum here, so I'll stick to the abbreviation there. The internet is awash in data and information. And the postulate here was that the amount of energy needed to refute BS is going to be orders, if not order, at least an order, and if not orders of magnitude bigger than that needed to produce it. So it's very easy to produce BS and to populate it on the internet. It's not that easy to actually refute it. And thereby the creator of the BS has an order of magnitude advantage here. And if we just think of a similar law in terms of recognition of good data, we have this, I'm just replacing refute BS by reject bad data and produce bad data at the other end. So I think in the long run, this is going to be the fundamental issue around which we will get advantage to the attackers versus advantage to the defenders. Now, having said all this, I'm going to turn, I'm a security person. So, of course, we would like to apply any new technology to security and also figure out what the consequences of that are for creating security vulnerabilities. So here is our take on how we look at the big picture of holistic security. Security is not yet being addressed in a holistic way, even though there's a lot of research on security, even though every organization has some practice of security, and there are hundreds of vendors and hundreds of startups in this area. They are mostly looking at point problems rather than at the holistic problem. And academia has to take some lead in developing a discipline of holistic security, which we are completely lacking right now. So in our work, we see at least three aspects to holistic security. The first one is resilience. We have to assume that breaches will take place and will persist. And we have to be aware of attack. Now, the work that, for example, I'm just picking on her because she was a speaker in this series earlier, Vijay, she spoke about coming up with policies. And that's a very, very important problem. But by definition, that is not considering attackers. It is considering policy, it's considering what you want to do rather than how it might be attacked by an adversary. So that is a traditional approach to security, and we call that attack oblivious. You're trying to design policy without explicit consideration of attacks and vulnerabilities. And that has been the traditional approach to security, and that has been largely what I have done in most of my prior work. But we now have this realization that you cannot continue in that mode. You cannot be attack aware. You have to be attack. So you have to have policies on how to respond to attack. It's not just enough to have policies in the absence of attack. You also have to understand what to do when attack occurs and is recognized, and how do you respond. And your response has to be measured. You cannot simply shut down the system and say we are going to scrub it and restart it in a pristine state. You have to recognize that the attacker is probably going to be forever persistent in your system. And any response you take is going to perhaps make it harder for the attacker to continue what they're trying to do, but it's also going to impact your legitimate users. So there's a big trade-off. If I shut the system down, yes, I prevent the attacker from proceeding, but I also prevent any useful work being done by my legitimate users. So this is a new, we are not the only ones talking like this. This has been talked about much more in industry than in academia. And among other academics, we would like to take some lead from the academic side in trying to address this question and come up with the theories and frameworks within which to address it. We also have this notion of zero trust, which has become a bit of a buzzword these days. But in the past, security has been based on static deterministic decisions. The kind of policies that Vijay gave examples of, the goal there is to come up with formulas that are going to give you a deterministic yes or no as far as access being allowed or not allowed. And the formula stays stable for some time until you choose to change it. So it's a static deterministic decision. There is an awareness that you need to bring in some dynamic aspect to these decisions, and the decisions may not be clear-cut 0 or 1. You may need some kind of a score so that you can set some threshold as to where you are going to allow access versus not allow access. And then there's this notion of continuous authorization. A lot of authorization today is based on, yes, I'll make the decision to let you in or not, but once you're in, and you can hang around and do activity. In fact, a lot of the models, you can continue doing activity indefinitely. So continuous authorization requires some kind of reauthentication, reauthorization. And then there's the notion, so there is a sophistication of access control models, which is required beyond what our traditional models are going to be doing. And then we need automation. We cannot do especially if you're trying to respond to attacks, you cannot bring humans into the loop. At machine speed, you have to be able to make machine speed decisions. You have to make decisions at machine scale involving hundreds, thousands, tens of thousands of users and computers. And you have to be smart about how you escalate decisions to human stakeholders. That's also very critical. And then you have to have the ability to rapidly change your policies. So AI is going to be critical to doing all of this automation. Without AI, we have no chance of doing any of this. But all the same, we have to have models that are amenable to adaptation and automation. So we have this general approach of when we look at security in an attack oblivious sense, we kind of break it down. There are many different ways of doing it, but this is our perspective on it. I'll just illustrate this by giving you a concrete example of how these different layers come into play. So suppose our goal is simply that we don't want our users to keep having to enter user ID password repeatedly while they are doing their activity in the enterprise. Let's just take an enterprise as our example. So you want to give some kind of single sign-on or reduced sign-on ability for users, because re-entering your authentication credentials repeatedly is very cumbersome. And it's a reasonable goal, and most organizations would try to do that. And that's a very high-level goal. In order to make it more precise and more rigorous so that you can actually implement it and enforce it, you have to come up with more detail. So the detail given here is that you're allowed, if you're authenticated in one place, you're allowed to go to its neighboring places. That's the one-hop lateral movement that you're allowed. But you're not allowed to go beyond the one hop. Now you can string together these one hops and get all over the network, but you got to do it one hop at a time. So if you're on any one machine, any one server, you can go to all the adjacent servers without authenticating again. And from there, you can reach further. So this is a very typical kind of assumption in, it's called lateral movement. It's called credential hopping. And in order to do that, you're going to have to keep your credential at the machine where you're currently logged in. So that it requires some caching of your credential and the ability to use the cached credential to do the one hop. And that's all fine. This is attack oblivious. Now, when you bring the attacker in, you recognize that if you're going to be caching credentials, it is possible that the attacker is going to be able to misuse those. So in credential hopping, the assumption is that somehow the attacker gets hold of one user credential on one machine, and then by using lateral movements can go across to many other machines and possibly exploit other user accounts along the way. So once you bring this, so here you're starting to be attack aware. You're starting to say, all right, without being attack aware, we relied on caching credentials, but we got to recognize that it introduces a vulnerability. And now you have to think about how to respond. So from attack aware, you have to get to attack resilient, because just recognizing the attack and the vulnerability is not enough. When you actually suspect that one of your accounts has been compromised, what are you going to do? Are you going to shut down that particular server? Are you going to stop all authentication? Are you going to say no more one-hop lateral movements? So there are different ways in which you can respond to the detection of such an attacker or the suspicion of such an attacker. And that's where it becomes attack resilient. So what we are really aiming for is multi-layer attack resilient security. And we are very far from being able to do that today, because it's a goal that a lot of people in industry would subscribe to. But we are still, in terms of especially academic research, we are still very new at trying to attack this problem. And we do need a lot of AI to do this. And we need AI at a lot of different levels. So our vision is that your attack and vulnerability surface actually extends across all of these layers. Now, you say, I want to minimize my repeated login. And if I cut down the lateral movements allowed because of one hop lateral movement due to credential caching, I can eliminate some of those links. But the consequence of that is not going to be just on the attacker. It's also going to reflect on the legitimate users. So we have to come up with some calculus for balancing these things. And a lot of actual attacks are going to occur at your implementation layer. However, the vulnerabilities that arise, that give rise to those attacks, require reconciliation at your policy or your goals layer. So the higher up you're in this abstraction stack, the more it's about fixing vulnerabilities caused at the lower implementation layer by adjusting these higher level policies. And the actual runtime attacks are mostly going to occur down here, and they're going to need responses at machine speed. And that's where you need to bring in artificial intelligence. You need to bring in artificial intelligence on how to respond by adjustment of policies at the higher layers, and how to take these adjustments and sort of drive them down to the implementation. So all of this is stuff that needs a lot of work on. And I'm going to stop with these two takeaways from this talk. If we hope to contain the asymmetric advantage that defenders always have, we need to address the data poverty problem. And even with data abundance, we need to address the good data recognition problem or the BS elimination problem. And we need a scientific discipline for multi-layer attack resilient cyber systems, which is necessarily going to incorporate artificial intelligence at all these layers. So I'll stop with these two takeaways.
Thank you so much, Ravi, for a great talk on holistic security and how the data poverty problem is affecting our security posture. There are several questions. I think we can have one or two of them, and then we can move on to the panel discussion. Maybe we can, one of them is about how can we protect large language models and the associated machine learning infrastructure for LLMs and GenAI from such attacks, and how you think that AI can help in that process as well.
Yeah, so, in a circular way, maybe LLMs can be used to protect LLMs, if you want a recursive kind of argument there. But I think in your opening remarks, you had pointed out a number of places where LLMs have clear vulnerability. You had also, which need attention. You had also pointed to Ken Thompson's observation that we have to trust the coders, not just trust the software. Well, it's not enough to just trust the coders. There's a whole supply chain. There's defects in the Trojan horses can be introduced anywhere along the supply chain. And Ken Thompson also has that famous Turing Award talk on trust and trust. And he has argued that if you embed the Trojan horses in your compiler, if you embed it in your firmware, it's going to be very hard to discover it, because any attempt to discover it, it's going to hide itself. It's going to make it look as though everything is normal. And that was a paper published in the 1970s. It's, that problem has not fundamentally changed. So I think one has to take somewhat of a holistic approach. It's good to focus on point problems, because ultimately in a holistic way, you have to bring all of them together. But unless you bring them together and still recognize that there are some weak points along the way,
Sure. Thank you.
In a nutshell, you have to take a holistic approach. You can't just and which is the most important problem the most important vulnerability to deal with at any point in time is going to change, because the attackers are going to come at the weak points, and those weak points are always going to change, because if you make somebody, all you're doing in security is shifting the weak points around. You're never completely eliminating them.
Sure. Yeah. Thank you so much, Ravi, and it's a privilege to have you on the call. So I think right now we'll then move on to the panel discussion with Q&A coming in. So we have. Let me open the panel up through different questions. One of them is. Have you looked at the performance degradation of the LLM as you add noise to X? So X in the sense, I think here, I think it's referring to Jie, to your presentation. I believe the question was that if you add noise to the data objects X, how does the performance of LLM degrade?
Okay, so my understanding is that the perturbation of the input can happen in both stages, the training stage and the inference stage. So it's going to be a little bit different. So let's first talk about maybe training stage. So in the training stage, if we inject perturbed X, what it will change, influence is the trained model, right? So if so theoretically speaking, if the data and the perturbed data were in the majority mass of the data distribution, then it shouldn't create too much influence because of the the influence also brought by neighboring data points. But if the input data was far away from the data distribution, according to the recent studies on the backdoor and the related understanding, it's possible that the model will be heavily influenced, especially in the regions related to the perturbed input. So that is behind the several recent advances. One is about backdoor understanding and defense. Another is about the watermark. The watermark actually leverages that observation to create some perturbation, so that if the owner of the watermark knows how to perturb in a right way, then the outcome of the large model will be used to certify that this is that owner, because it's creating what is targeted output. So this is the idea. Yeah, so that is about training. But for the inference, it's a little bit different because the model is already trained. So it really depends on whether the perturbation happens in the data-rich region. So if it's a data-rich region and with a reasonable smoothing, it's possible to defend against the adversarial application during the inference. But if it's a bit in probability distant from the training data distribution, then it's hard to say. So the perturbation can theoretically target any wanted target, like manipulate the output label to any wanted outcome. Yeah, I hope that gives my.
Thank you. There's another related question, is there a way to calculate or project the accuracy of loss based on the noise injection level to decide what should be a sufficient level? So I think the questioner here is looking at can we project the I think loss of accuracy perhaps there, and based on the noise injection level. Like how much noise should be injected especially in an LLM kind of setting, that would ensure that can we use that noise injection level to project the loss of accuracy?
Okay,
More
so
with
the
that,
question
yeah.
is, my understanding is that whether we can inject the noise to identify the accuracy. Let me just, I'm still trying to understand the question. So
Yeah, I think I'm also trying to understand the question, but the question states as follows: is there a way to calculate or project the accuracy of loss based on the noise injection level to decide what would be a sufficient level? All right, we can come
Okay.
back later.
Yeah, my guess is related to the accuracy in the robust sense. That is when we do the inference, if we add some perturbation, what is the worst case accuracy? So if the perturbation is in the most adversarial direction of perturbing the input, what will be that accuracy? Yeah, I think it's reasonable to consider using different levels of noise injection to identify the robustness.
Great, thank you. Yeah, so there is one question that is coming up on: can the panel comment on the use of generative AI, in particular LLMs, for both malware detection and malware analysis? So I just want to quickly comment on that and then open that up to the panel. That yes, we have an internal project going on with respect to malware analysis using LLMs, and we can discuss that further internally. But let us hear from the research challenges and issues with respect to malware analysis and malware detection using LLMs from our distinguished speakers. So who could go?
Ashish, can you remind me the detection part? I didn't hear.
Yeah, so the question is that can the panel comment on the use of generative AI, in particular LLMs, for both malware detection and malware analysis?
Sorry, what is the first word? What detects?
Malware detection. So given a
Malware. Okay,
malware code,
malware, yes.
or given a set of code repositories, for example, or binaries, can you detect which one of them is a malware and which one of them is not, with respect to sufficient level of confidence?
Yeah, I'm not an expert in this area, but I can just share my personal view. So I think since it's a detection problem, let's first talk about the malware detection. It's a detection problem, so it's reasonable to set up it as a hypothesis testing framework that we want to control the trade-off between the detection power, and the false alarm rate. So in doing that, I think there are just generally two ways. One is to generally what people do is to collect enough clean data. That means the code reports that are definitely safe as the null data, and then train some null distribution on top of it, and then construct testing to see whether there is a significant deviation from that. I think the challenge would be whether we can cover sufficiently the space of all the the code reports that we want to cover, right? So yeah, so actually, can you remind me if the question is only about challenge, or we want also to talk about the potential solution?
It can be a potential solution. It's up to you. Yeah.
Okay. Yeah, I think a possible solution of that is to set up in a distributed way, because different people really access different kinds of reports because they have different domains of interest, right? So I think it's reasonable to have this distributed or decentralized architecture of the detection, that each team will use its own clean data report to set up the null distribution, and then we have a way to combine the test results. So there is some existing literature of like distributed hypothesis testing to combine the decision results without sharing the data, and just sharing the statistics or even the final detection results, right? Combine the p-value is also a huge field in statistics for that purpose. Yeah, that's my personal.
Thank you. Yeah.
Thank you.
I think we'll move on to another question that we have received. I think this is specific to Ravi's talk. So the question, this is how the question is stated. So thank you for offering these great research presentations. The question I have is, do you think defining security concern domain-specific ontologies can assist with adapting and articulating goals as part of identifying and refuting BS scenarios?
Well, I'm trying to parse that question into its pieces.
Sure, Ravi. So let me also bring it up myself. Is that the question is I have is, do you think defining security concern domain specific ontologies? I think the question is asking that can we
Right.
use maybe LLMs or similar capabilities on defining security concern domain specific ontologies? Number one. Number two, can it assist then with adapting and articulating goals as part of identifying and refuting BS scenarios?
I think that's an unknown. It would be desirable to do that. Now, has it been done? Can it be done? I think probably, has it been done? I would say no. Can it be done? Hopefully it can. But, in terms of domain specific, the biggest amount of BS is in the political space or in the space of conspiracy theories and places like that. Beyond that, how narrow you can make your domain and how much of a real threat it is for BS in very narrow domains. So I'm speculating. I think it should be possible to do it.
Okay, yeah. Thank you, Ravi. So there's another question from Saswat is on that. How do you use this effort fitting with what is available at NIST cybersecurity framework and OWASP? I don't know exactly what effort he is referring to, but maybe he's referring to this again, security concern, domain specific ontologies, and NIST cybersecurity framework and OWASP, and how LLMs are helping in that process. Okay.
Well,
sure.
We are just starting to think and look at how LLMs can be used in security. So our thinking on this is still very early stage. Optimistically, they should be useful. And if you say that a lot of your low-level implementation level responses, which need necessarily to occur at machine speed, those, there's no human interaction there, but there has to be a recognition in your automated system as to when decisions need to be escalated to a human stakeholder. And but when they are escalated to human stakeholders, you need to present them in a form that's appropriate. And that's where sort of LLMs and generative AI and all that can help. So even recognizing when to do the escalation to humans is a very, very critical thing. And I'm not sure at the implementation layer itself. Certainly deep learning can help. But whether LLMs can directly help there or they help more in the escalation phase and then the coming back from the goals from the high level stakeholders down to the implementation layer, that's probably where they can be most effective. But this is a very speculative answer.
Thank you.
Ram, do you want to add something to that?
I mean, I agree with what is said. I feel that generally the biggest gap is in from what an algorithm makes a decision with respect to probabilities to making a higher level decision. That semantic gap is a big gap, and a lot of decision automation work is looking into that kind of problem, right? It's one thing to say we are looking at rating an image as whatever, right, cat or dog, but it's another thing to give a probability on a very complex question and then asking a different system or a human to make a decision. I mean, that's a big semantic gap right there.
And anyone else from the speakers?
Actually, there was a paper presented at the DBSec of this year by Latifur Khan, Anup Singhal from NIST and others. So they were actually using BERT to actually, from the CVE, that is the common vulnerabilities and exposures database, using that and using the semantic context, how to actually detect ATT-CK, and then they're actually categorizing the adversaries, like the tactics, techniques, and platform procedures, like the TTP. So this is an interesting piece of work that is along these lines. They have these ontologies of vulnerabilities, that is the NIST framework, and how can you actually use large language models to actually extract them and extract them into ATT-CK. So that is an interesting paper to look at. So.
Thank you. Thanks a lot, Vijay. Okay, so I think we'll move on to another question that is related to that is actually for Srini particularly, how computationally intensive is implementing PAC privacy due to repeated training of machine learning models on various subsample data sets, and maybe with respect to LLM.
Yeah, well, excellent question. So I want to say, in regards to the first question that was asked about perturbation, that I want to point out that it's potentially a win-win scenario. So people talk about generalizability of LLMs and generalizability of machine learning, and one way, obviously, overfitting is a problem. What you want is low generalization error and so on. So the repeated trials actually, people do this often with random dropout, subsampling data, and so on and so forth, in order to avoid overfitting and in order to reduce generalization error, right? So, so it's not that people don't do repeated training. I mean, there's a lot of iterations within the training that happens already. And the cool thing that I didn't get a chance to point out during the talk, but I want to hear, is when you have stability associated with whether it's perturbation of the input data set or subsampling the input data set, that actually gives you provably a better model from a generalizability error standpoint, right? So the overall goal here is it's a combination of how do we create a new machine learning training technique that essentially in stochastic gradient descent subsamples. I mean, there's subsampling that goes on in stochastic gradient descent all the time in every epoch. You want to utilize that subsampling, the entropy and that distribution to not only get your privacy proof, but also show, and the reason it's in there is to improve utility, improve accuracy, right? So I don't know how to do this yet, but the high-level answer to the question is I think it's win-win-win. You know, you could win in terms of generalization error. You could win in terms of privacy, and well, at least you're neutral in terms of efficiency. Right now, we have to repeatedly run a bunch of trials. So when we've done our experiments, as I mentioned, we do medium-scale experiments because we run training, you know, several times in order to figure out what perturbation to add, right? But we are hoping to improve the situation, and you know, things are looking better this month than they did, you know, back in March. So.
Thank you. Thanks, Srini. There's one more question on PAC privacy. So PAC privacy seems very computational intensive. Can you compare the computational resources between the PAC privacy versus differential privacy?
I mean, we've taken human work in terms of writing, you know, a 10-page proof for an algorithm, for example, k-means. That's a clustering algorithm. You know, people have written a paper that has long proofs in it to show a differentially private version of that algorithm. Okay, so this is something that people do all the time. They take an algorithm and then they differentially privatize it. When you have complicated algorithms, you have to approximate, and there's issues there, but I don't want to get into that. What we've done is we've taken that work and we've said that's going to be computational work. That's going to be repeatedly running the algorithm. And if the algorithm is, you know, is k-means clustering, you can run it many times with different random initializations. That already happens now to get better results. And we're using that as a black box. We're using essentially the algorithm as more or less a black box to go compute the noise that we need to add in order to get our provable metric, right? So we've just kind of flipped things around. So I guess, you know, the glib answer is, well, humans took much longer. And now we're translating that to computers. And so, what do you care if you have 100,000 processors running for a day? You know, at least it's not 100,000 humans working for a day or a few hours. But I think the perhaps to be less facetious, this estimation thing, the Monte Carlo estimation thing, and the random trials is a problem with PAC privacy that we're trying to address. And I think we can do it in order 1 trials and keep that constant down. And so we have some work that's ongoing. So, you know, stay tuned. But it's a great question. Thanks.
Thank you. So Srini, on that context, I have a question around that about with the prompt engineering and the whole natural language based queries that we have for ChatGPT and other LLMs. How do you think PAC privacy can be enforced on these prompts and the responses from LLMs so that privacy can be appropriately enforced?
Yeah, so, you know, excellent. So basically it's more of an inference problem as opposed to a training problem, because I mean, you know, prompts are the model has already been trained, and you're now essentially trying to you're trying to protect the prompts. There's so many privacy considerations here, Ashish. Right. I mean, it's the privacy associated with OpenAI wants to protect ChatGPT parameters, right? And there's the training set, which is what I talked about, which obviously, you know, that's going to get exposed by the model parameters, and then the model parameters get exposed by the inference queries, right? So you have to parse this, I think, out and then kind of address things, because I think it's a little bit different depending on what you want to address. It's a little bit different. Oh, I must say that the prompt itself has privacy associated with it. If I'm asking about something sensitive about myself, and the question is, you know, how do you protect that, you know, from OpenAI or what have you, right? So I'll give you my take, right? This is not a universal solution. I think that you can do you can protect the prompt by using cryptographic techniques. and essentially, multiple ways. You can say the LLM is running inside of an enclave, inside of confidential computing, and the prompt goes to it encrypted, and then you get back an encrypted result, right? I mean, that's one way that you can actually do right now, right? The other way is to use cryptography, and I think that unfortunately isn't quite practical for LLMs, but you can do it for other inference, where you encrypt the query and then you get an encrypted result back. I mean, not necessarily fully homomorphic encryption, but something more lightweight. So now for the last part, and I'll stop. Training data is sensitive. It leaks into the model parameters, and the model parameters leak out with respect to the prompt responses, right? There, you could use differential privacy or pack privacy to solve that problem. And we're not quite there yet for the scale of things that I think we need to do, but certainly there's research that is helped with simpler tasks. You know, I joked about medium scale models, but I think that's a reasonable statement, that I think you can do that for reasonable scale models, the medium scale models.
Thank you so much, Srini. So on that topic, Ram, I think thank you for joining us, and even though you had a class. So one of the problems with respect to access control and deep learning based access control is how do you ensure that insider threats and their access control is appropriately managed, or insider threat or access control can be appropriately managed to protection. For protection against insider threats in an enterprise network. How do you think LLMs can be used in that context in an effective manner? Ram, I hope I'm not putting you on a spot, but
no, I mean, obviously we are all speculating to a certain extent. My thought is that in general, we have done some work on using machine learning for automating or semi-automating access control, right? One of the challenges there is when you're dealing with traditional access control approaches, you have strong controls over information on which you make decisions, using which you make decisions, right? So think of attributes, roles, etc. You use that information, and that information don't just come into being arbitrarily, don't get changed arbitrarily. So these are security relevant information that you use. But when you're using modern machine learning techniques, I think Ravi mentioned about the BS hypothesis, you have this problem where you're utilizing a lot of information that is not meant to be used for making security decisions. So unless you are able to really control and what's the right word? You really need to have quality control on the information on which the model is being trained on, and it's utilizing to arrive at certain kinds of recommendations at that time. So in our work, for example, we have used system-wide metadata across the stack from upper layers to lower layers. Let's see if we can access, extract metadata from across the system and use that metadata to inform access control decisions. But the challenge there is, again, unlike regular information, this metadata is not quality controlled. So you might be making decisions on data that are easily tamperable, that might misrepresent, and you might be able to exploit that to get access to things or deny access to things that otherwise traditional access control systems might do. So there are challenges there. As much as there is power in automation by using advanced machine learning techniques, you really need to worry about the quality of the information on which the model is trained on and it is using to make decisions at runtime. So I'll leave there and possibly look for any other comments.
Thank you. Thanks, Ram. Any other thoughts on that, and maybe on the policy aspects, maybe Vijay, or like just to clarify the point here is that how can we generate policies automatically for protection against insider threats in a network, and with using LLMs, for example, and enforce them in a machine enforceable manner. I think so. I know there's again There's a new line of work, and all LLMs are pretty new. And perhaps we'll have another summit sometime later when we'll have more, the work has matured. But I think this is a good set of seeding our mental thought processes within Cisco, and I hope outside Cisco in this process. But anything that you'd like to share?
Yeah, I think even without using LLMs, we should first have to come up with a solution, so using LLMs is the next step, of course, that may speed up the process, or, because as Ravi mentioned, it is a dynamic system, you have to react to what are the vulnerabilities and what is happening now and change the policies based on that. Right now we are in a static mode, really. So to incorporate this dynamic loop, of course you need faster detection techniques and then deployable techniques. There, LLMs can help us, but we need to have a way of extracting even without using an LLM, some sort of an approach to react to these threats, vulnerabilities, and so on, So I think we have to begin there.
Okay, yeah, thank you. And I think the natural language descriptions around the context and different aspects of insider threats would be very useful. They are not readily available today. I think there's one question that we can take right now is, there has been a lot of work on jailbreaking attacks on LLMs. Do you have any thoughts on how to mitigate these attacks and how effective mitigation tactics are likely to succeed over the long run? Anyone who would like to?
Yeah, so this is speaking with confidence, given my naivete. But I was going to say that, it really goes back to what have these LLMs learned, and they've learned from the data, right? The data is obviously, there's lots of redundancy. There's maybe corrupted data, maybe there's adversarial data. And you are creating a model, from this, terabytes or petabytes of data, and this is true even for deep learning. And you end up with this network that has these corner cases that corresponds to these adversarial cases, right? So people have actually looked into differentially private perturbations on the image recognition, the networks, not LLMs, because they haven't gotten there, and shown, not all the time, but on average, the resistance to adversarial examples is higher, right? And why is that? Well, the reason is because there's a certain amount of stability associated with differential privacy. When you've created something that's differentially private, you're basically saying it's hard for the adversary to distinguish, from this one, let's say, a data element that was used in an adversarial way to go train the model, right? That actually differential privacy essentially says that you can't do that. I mean, with a high degree of confidence. So I think there's a deep relationship between adversarial robustness and privacy in relation to exposing the sensitivity of data, right? And as I mentioned, I think there's a relationship to generalizability as well. So I'm very excited about kind of going deeper into the training process associated with not necessarily LLMs, but neural networks and machine learning in general, and trying to disambiguate these notions of robustness and privacy and integrity, etc. And I think there's, like I said, I think there's a real deep relationship, right? But I don't have much more to say.
Thank you, Srini. The last quick question we have from Harun Iyengar is, the question is, the attacks on LLMs which can cause them to reveal harmful and private information, especially this is again related to jailbreaking. I think how do you think we should address this data exfiltration attacks on LLMs or data exposure from LLMs can be addressed, or any thoughts around the last one line each on that, please.
I can share my view on that. I think, yeah, this is a great question. The jailbreak, as far as I know, there is no clear definition of it, right? I mean, mathematical definition of it. So my view of it is essentially it's a kind of backdoor. So because the prompt input into the LLM is a bit weird, that is not typical, the data that were originally used to train the model. So that fact, that region of data scarcity can be exploited to create a surprising outcome. But if the model is trained on sufficient amount of benign data in those regions, then it will be automatically smoothed out. So I think the key is really to understand the regions where the model will behave badly. So we need to understand at some latent space, what are the regions that there is some discrepancy between the trained model and the wanted model. So yeah, so a couple of things to do, in my opinion, include, for example, set up the training data that can cover as much space as possible. So it's less likely to backdoor those regions and create a surprising outcome. The second is to maintain the security in a continuous basis. That is, whenever we have new data that we want to build into the trained model, so that the model can get security updated. We want to do it in an online fashion, so that you will not forget the previous security characteristics. So that's related to the continual learning I mentioned, and also the part that that is about diagnostics of the regions that is risky. So even before the attack, we want to know that these are the regions that there is a significant deviation between what we want and the actual model. So yeah, the thing that I mentioned last, I didn't have the chance to cover the technical detail, but the main idea is basically to set up the comparison contrast between the theoretically predicted probability of that model and the actual frequency of words in those regions. So if there is a significant discrepancy, there is a high confidence in a rigorous sense, right? Statistical sense, high confidence that we need to fix that area. So this is.
Thank you so much, Jie. Yeah, really appreciate it. I'm sorry to interrupt, but we're at the top of the hour already, 2 minutes past the time. But thank you so much, Jie. And thank you so much, Srini, Vijay, Ravi, Ram, and Jie for joining us for the Cisco Research Summit on LLM and generative AI and security. It's a great honor and privilege to have you as distinguished speakers on this very highly evolving topic. We had a very good balance of quantitative and mathematically deep discussions, as well as qualitative aspects of LLM security. Sometimes we discussed problems and challenges that are a little bit away from LLM security, but I think that's important, because we are in the process of this new era of LLMs, and therefore we'll slowly bring in concepts and topics from other areas into LLMs, and vice versa as we go forward. Thank you so much again for everyone to join us, and thank you again, the great speakers we had. Really appreciate your time.